In this devlog, we'll be taking a look at the performance of our backpropagation function by examining what the network is spitting out and trying to compare it with the current input. So, or rather, the actual targets, rather. Okay, so I was actually playing around with it earlier today, and I created two functions: void print input to console and void print output to console. So I think I should. Well, the way it works is that print input to console simply just takes the input and then prints it out as a vector of values. I think I should add another function called print targets to console. So print target to console, or target to console, okay, which works the same way as print input to console. Okay, so I just copy this. Okay, and then just replace input with target, and then print target to console. Okay, so all this function is doing is that it's looping through the target variable and printing out the target values. So what I'd like to do is I'd like to compare the output. I have a function here called print output to console. Okay, so I have print output to console, which just takes the output values at the index of output layer, okay, which is at size -1, and get the matrixify activated values. Okay, so the activated values of the output layer, and then just print it out to the console. And in my main function, so instead of I'll say output and I'll say target. Okay. So in my main function, I after printing the error, I print out the output, or what the neural network's guess is, and I'll print out the target, or what the actual value, the ground truth, or the value that the neural network is trying to achieve to the console. Okay, so I've been playing around with it. Let's see if this works. Okay, so in my main function, I iterated through 100 iterations, and if you notice, it actually performs poorly. Well, the reason behind that is I think I was playing around with the cost function in set errors. Okay, originally the set errors would use a cost function of, let me comment this out, this one, the activated value minus the target value. Okay, so if I recompile this, now it performs better. After 100 iterations, we can see that the output 0.8 is approaching 1, right? From 0. You can see it changes right there. And this one, the middle one, approaches 0, and this one is trying to approach 1 as well. So it's learning over 100 iterations, and if we increase the iterations, the number of iterations, say 1,000 iterations. Okay, we can see that it's slowly trying to replicate 101, because it's trying to learn 101. So I guess the backpropagation algorithm is working in this case. It's learning at some extent. So what we'll do is we'll try to improve on it, because I'm not really confident that's how the backpropagation is implemented, or the cost function is implemented. So what I'll do is, sorry about that. What I did is I did some research, and the cost function should actually be implemented as 1/2, or at least the quadratic cost function is implemented as 1/2 times the sum of the I wasn't entirely sure if it was activated val minus the target, or the output minus the target, right? So we'll try that out. We'll try the quadratic cost function, wherein the quadratic cost function is defined as the as 1/2 times the sum of square difference between the activated val and the target val. Let's see if we get some good results. So in C++, we can do the square function or the exponent function by using the pow function. So in this case, we square it. Okay, so we square it. And then we assign it as temp error, do a summation, and then before ending, we say this error is equal to half, so 0.5 times this error. Okay, so let's see if this function works better. For 1000 iterations, okay, so let's see the difference of I think 0.06, 0.06, and 0.0004, right? Okay, if we did it that way, you can see that it actually performed poorly. It actually learned the reverse. So it's a neural network that attempts to learn it's a neural network that trains itself to learn the exact opposite of the target. If we were using that cost function. So the cost function has the lesson here is that the cost function has a big effect on the back propagation. And so let's try to analyze why. So maybe I implemented the quadratic cost function incorrectly, or maybe I shouldn't put the exponent there. So maybe it should be something like this. Okay, add it to the error because we know this works quite well. And then before adding it to the global error, maybe this is where I'll perform the exponent. Okay, and then before halving it. Yeah, let's try this. So what I'm doing right here is that for the individual errors, comparing the output and the target, it will still follow the output neurons at activated val minus target, store it in the array or in the vector of errors, and then before adding it to the global error, I raise it to 2 or I square it. Okay, and then before multiplying it to 1/2 or 0.5. So let's try that out. Okay, so this one actually performed better. See, it approaches 101. Okay, so maybe this is a better implementation of the cost function. So in this case, I'm doing a quadratic cost function for the global error. Okay, where it's implemented by having the individual errors as the output value, the output activated value, minus the target or the objective, storing it to the array of errors. But for the global error, I'm performing a summation against the square difference of that error before multiplying it by 1/2, okay, for the total global error. Okay, another nice thing we can probably do is print the historical errors. Okay, and then probably try to create a nice graph out of it. Okay, so we have an array called historical errors, and what we can do is, going back to our neural network, we'll have another function called void print historical errors. Okay, and then in our neural network, we can implement that function as print. Print. Okay, print historical errors. Let's move a bit down here. Neural network, print historical errors, and what we'll be doing is we'll be looping against all the historical errors. well, you have to check, right? If I is equal to, or is not equal to, this historical errors, that's size minus 1, then include a comma. And then end line. Okay. And then in our main function, after doing the loop, we say, rather say print historical errors. Okay, let's try this out. Okay, loop 1,000 times and print historical errors. Okay. Okay, that's a lot. Oh, it's a lot. Let's run it in original resolution mode. What I'll do is I'll copy all these errors, and then I'll open up a spreadsheet. And then paste those errors there. Or, maybe I can just go to the desktop. Open up a errors.csv file and paste all the errors there, and then open that file with LibreOffice. Open. See if I desktop errors.csv. Okay, now it's in a nice formatted fashion, so we can, what we can do is we can graph this using a line graph, right? A line graph using straight lines, pointed lines. Right. Okay, so this is our errors, our error rate, or our error performance, or back propagation error performance. Oh, sorry about that. Let's extend this. Come on. There we go. Okay, so as you can see, the error rate drops rapidly. So I guess we're implementing back propagation properly. Right? These are the historical errors. So you can see that the neural network is getting better and better until it reaches a very small number. Okay, so for this video, all we did was we validated that our backpropagation algorithm is actually working. Okay. That's it for this devlog. The only change we had here is that we used quadratic cost a function for, or rather, yeah, we use quadratic cost function. And then we push that to GitHub and end our session there.